Hi, good morning, everyone. Thanks for dialing in this virtual presentation. My name is Anna Luo. I'm an applied scientist at AWS SageMaker. It's my great pleasure to present here today at Ray Summit. Let's start with the content of today's presentation. In principle, we will have two components. First, we will talk about what is Amazon SageMaker. And we will use reinforcement learning as an example to demonstrate how to build a typical reinforcement learning/machine learning workflow in practice today. And then I will introduce you how you can run Ray and RLlib seamlessly on Amazon SageMaker, together with the ability to scale and save your cost with Amazon SageMaker plus RLlib. In the second part of the presentation today, we will focus on a real-world reinforcement learning use case. Specifically, we will talk about inventory management problem. I will walk you through the problem dynamics as well as the formulation. And I will introduce you how can we use historical data to construct a simulator so that the RL agent can use to develop its policy. Most importantly, I will introduce what are the states, action, and rewards in the formulation of the corresponding Markov decision process. Last but not least, I will demonstrate some preliminary experiments results that we got using both RL reinforcement learning agents as well as the traditional operations research algorithms. In the end, we will finish this presentation with a quick recap. So let's talk about Amazon SageMaker first. What is Amazon SageMaker? It is a fully managed service that provides every developer and scientist with the ability to build, train, and deploy machine learning models quickly. It provides an integrated Jupyter Notebook interface for easy access to your data source for exploration and analysis, so you don't have to manage servers. It also provides common machine learning algorithms as well as Ray and RLlib for reinforcement learning, and I will elaborate that a little bit more later on. You can deploy an RL model into a secure and scalable environment by launching it with a few clicks. So in a nutshell, we are making it easy for you to build, scale, and apply your RL model in practical. So before we dive into the service itself, let's just look at what it actually means to build a typical machine learning workflow in practice today. Unfortunately, it's a pretty difficult task, and you have to go through a number of different steps. There are so many tools that you can use for each of them, and everything needs to line up perfectly if you want to build a successful model and deploy it. So of course, first you need to prepare a data set. You need to annotate and clean and transform data, and then get your training set ready. For reinforcement learning, this usually corresponds to the process of developing a simulated environment. Once you have that, you can start with experimentation. You can start with trying out different algorithms. In this case, you can use the suite of state-of-the-art algorithms that RLlib provides. Then once you start to figure out which algorithm is going to work, you need to try different parameter combinations. That requires a bunch of infrastructure. No one actually wants to manage that, but you have to do it to power those training jobs. And then you need to tune them. You need to extract every bit of accuracy from those training jobs in order to get the best possible model and the best business outcome. Over the time of the project, you're going to end up with training numbers of thousands of jobs, and it's not easy to recall what you did last week. Once you have had a model with satisfying performance, it comes to the hardest component, which is deploying that model in production, where it can start making the actual decisions from the request that your business apps send to it. So as you can see, although people tend to focus a lot on algorithms and neural networks and distributed training, there is quite a lot of stuff that needs to be done if you want your RL project to be successful. This stands in the way of achieving your expected outcome, which is the purpose of Amazon SageMaker. In last re:Invent, we expanded on SageMaker and added a bunch of new capabilities. In addition to reinforcement learning specific offerings, we will look into the Spot Institute today. As an RL practitioner, you may wonder why Amazon SageMaker can be a good place for you to hold your RL workflow compared to other cloud-based machine learning services such as self-managed Amazon EC2 and AWS-managed Amazon EKS. You must consider the infrastructure, operational, and security costs for each step of your RL workflow, as well as the size and expertise of your RL science teams. The total cost of ownership is often the financial metric that you use to estimate and compare machine learning cost. And the detailed total cost of ownership analysis conducted earlier showed that Amazon SageMaker provides a better total cost of ownership across teams of all sizes. Specifically, that's 54% lower than EC2 and EKS over 3 years. With self-managed machine learning with EC2, you take on the responsibility of provisioning and managing EC2 instances, including instance failure recovery, patching, automatic scaling, and building and maintaining request security and compliance. You can use the AWS deep learning armies with the machine learning frameworks and libraries previewed, which is also provided in Ray. But you still need to optimize data access to get high throughput and also optimize your setup to scale up. In contrast, Amazon SageMaker is fully managed. You don't need to build, manage, or maintain any infrastructure or tool to support RL. Amazon SageMaker also runs your model on auto-scaling clusters that are spread around multiple availability zones to deliver both high performance and high availability. Because you pay for storage and network based on your usage, costs are controlled. Amazon SageMaker has built-in security and compliance for machine learning models, so you don't need to invest in additional security. Training and hosting are built by minutes of usage with no minimum fees and no upfront commitments. You can also use Spot Instance to take advantage of unused compute capacity in the AWS cloud, just like what you can do with native EC2. Now let's move to reinforcement learning specific part. Amazon SageMaker RL builds on top of Amazon SageMaker, adding pre-packaged reinforcement learning toolkits and making it easy for you to integrate various simulation environments. As you would expect, training and production infrastructure is fully managed, so that you can focus on your RL research problem and not on managing servers. Today, you can use containers provided by SageMaker for both TensorFlow and PyTorch that includes OpenAI and RLlib. As you roll with Amazon SageMaker, you can easily create your own custom container environment using other RL toolkits if necessary. In terms of the RL algorithms, we support code from Intel, Ray RLlib from Anyscale, and OpenAI baselines. Users found Ray RLlib handy for large-scale reinforcement learning experiments. When it comes to simulation environments, Amazon SageMaker RL enables you to connect to various types of simulators. First, it supports first-party simulators such as AWS RoboMaker, as well as other open-source simulation environments that are developed using OpenAI interfaces. For example, Energy Plus for HVAC and PyBullet for robotics application. You can also build your own custom environment so that you can code this up and bring that into SageMaker RL. As a matter of fact, this will be the case in the second part of our presentation today, where we build our inventory management simulator and bring it to Amazon SageMaker. Lastly, you can also connect to commercial simulation environment, such as MathWorks simulants, if you're doing manufacturing type of use cases. As a current Ray RLlib user, you may wonder what you can do with your RLlib models/algorithm on Amazon SageMaker RL. So first of all, you can train your RLlib models with managed Spot instance seamlessly as what I mentioned before. Let me explain this a little bit. So managed Spot instance uses Amazon EC2 Spot instance to run training jobs instead of on-demand instance. You can specify which training jobs use Spot instances, as well as a stopping condition that specifies how long SageMaker waits for a job to run. Metrics and logs generated during training runs are available in CloudWatch. Spot instance can be interrupted, causing jobs to take longer to start or finish. You can configure your managed Spot instance jobs to use checkpoints. SageMaker copied checkpoints data from the local path to Amazon S3. When the job is restarted, SageMaker copies the data from Amazon S3 back to the local path. The training can then resume from the latest checkpoint instead of restarting. Amazon SageMaker RL automatically configures your managed Spot instance jobs to use those checkpoints. The training can then resume from the latest Ray RLlib checkpoint instead of restarting. In terms of scaling, you can scale up your experiments with either homogeneous scaling or heterogeneous scaling. By homogeneous scaling, you can use multiple instances with the same type for a single Amazon SageMaker job. Whereas for heterogeneous scaling, you can mix and match different types of instances, for example, CPU plus GPU, and they can run in multiple Amazon SageMaker jobs. So these multiple Amazon SageMaker jobs will talk to each other and share resources that builds up this Ray cluster in total. You have the freedom to set up the cluster according to a specific use case. For example, whether you want to use multiple CPUs for rollout workers, collections, and the GPU instance, for example, to policy update. We also come with a collection of Jupyter Notebooks, just like Amazon SageMaker does. They are available on GitHub, featuring both simple examples like carpool, as well as the advanced ones in a variety of domains such as robotics, operations research, finance, and more. As you can see, we have different types listed there, and we have the GitHub repo listed there. So feel free to check out AWS Labs/Amazon SageMaker examples/reinforcement learning. So you can easily extend these notebooks and customize them for your own business problem. We will start with the specific folder called RL Resource Allocation Rate Customer Environments. So it focuses on operations research, and it looks at 3 canonical problems: bin packing, vehicle routing, and news vendor problem. We will select one, the news vendor problem, as the starting point, and in the second part of the presentation today, we focus on a specific branch on top of it, that's inventory management. Okay, with that, let's move on to the second part of the presentation today, real-world reinforcement learning, inventory management. Managing inventory levels is critical to supply chain sustainability. A clear relation exists between inventory levels and order fulfillment service levels. The role of an inventory planning system is to determine the optimal inventory level that should be held for different products. The systems attempt to balance the cost of meeting customer demand with the cost of holding too much inventory. Inventory level is reviewed periodically, and adjustments are made by either adding or removing the existing inventory through different means. Most retailers face this problem either in their stores or warehouses. At each time point, demand drains the inventory, and the extra inventory is carried over to the next period. If the retailer fails to meet that demand, it will either be marked as a backlog order that gets fulfilled at a later date, or simply chalked up as a lost sale with zero profit. And this typically describes the state evolution of a dynamic problem. Handling such a dynamic problem is challenging due to the curse of dimensionality. For example, online demands that comes in at each period is stochastic, and there exists clear cross-product correlation. Decisions are rarely isolated to a single period, and they are repeatedly and periodically taken and thus have a downstream impact. This makes the problem non-trivial. For large retailers in competitive markets, price matching causes abrupt and random changes in the price of a product during a decision. Besides, it is estimated through analysis of a large-scale survey that only 15 to 23% of customers are willing to delay a purchase when confronted by an out-of-stock page. This indicates that a lost sale assumption is more realistic in competitive environments rather than a full backlogging assumption. And again, by lost sale, we mean that they decide not to purchase anything when they found that the product is out of stock, where backlogging assumption assumes that a customer will wait for the product to come back. Last but not least, in reality, there often exists constraints across different products, such as maximum number of units that you can have at one time, and also the volume or similar capacity constraints. Due to all these complexities inherited in inventory models, researchers in operational research typically put certain assumptions for this problem. A classic formulation is the news vendor problem, which tries to decide on the alternate decision of a single product to cover a single period of uncertain demand. Carlin studied an inventory system with continuous demand density with lost sales in a constant lead time of 1. They showed that an order up policy, which means a policy that orders up to a target inventory level, is suboptimal in this case, even with linear cost structures. Janakiraman and Ram, they developed a convexity results for an inventory management system with lost sales, constant price, non-crossing lead times, and order up policies. Full backlogging is another commonly used assumption, which we assume any sales that are missed due to a lack of inventory or backlogged and filled up in the next period. As discussed in the previous slide, it is more realistic to assume only a certain percent of the customers are willing to wait for the product to get back. Besides, Nehemiah's formulate myopic policies for an inventory system where excess sales are lost and the lead time is random. So in summary, the multi-period and news vendor problem with lead times under the lawsuit model is known not to meet simple solutions such as an order up to policy. In order to apply reinforcement learning into this inventory management problem, we need to dive a little bit into the problem dynamics itself. So let's look at what would happen inside this inventory management process. So at each time period, the following sequence of events would occur. First, the features of inventory for each product is observed and replenishment orders are taken and filled according to available capacities. The underlying decision-making system can be either reinforcement learning or non-reinforcement learning. Then the retailer receives the in-flight inventory from the previous orders and also the current orders with 0 lead time. Then the customer demand is observed and filled using available inventory on hand. After that, the extra inventory is held at a holding cost. Of course, there are other price-related terms as well. For example, revenue, the purchasing cost, the holding cost is listed here, and of course, underage cost if we consider that. So this workflow is adjusted from this paper from House et al. In 2020, Origin, a reinforcement learning library for operations research problem. Once we understand the transition inherited in the problem, we're ready to formulate the inventory management problem as a Markov decision process. So it's time for some mathematical notation now. First of all, we have the state STI, that is the state for the Markov decision process for product I at decision epoch T. And ATI is a one-dimensional root number, and that's the action taken by the agent, and it makes a decision at epoch T for product I. So the superscript I is for a product, and the subscript T is for the epoch or time step. And we use capital T to denote the demand from the decision epoch S to decision epoch T. And note here that S happens always before T, so S is less than T. And we also apply this convention notation that when we talk about DTI, we mean the demand that comes in between T and T plus 1. Last but not least, we have ITI denoting the inventory for product I at decision epoch T. And more mathematical notation to come. We have the vendor lead times denoting the time you would need to wait for the product to arrive to the retailer. Therefore, it's a non-negative value. We have the price/revenue at time T for product I once you sell that product to the customer. We also have this cost term SageTI denoting the cost at each time T for product I. And we have this notion of FTI. It is a fill rate for product I at decision epoch T. It denotes the number of units that the vendor has available at decision epoch. So it is intuitive that the action larger than the fill rate level will be capped at the fill rate level. And this one you may be already familiar with it. Pi is the inventory management policy. With all those notations, what is the actual objective function here? And that corresponds to reward function in the formulation of a Markov decision process. You can see this long reward function. It consists of 3 different components. For the ease of understanding, if we look at the first part, we can understand it as the net revenue, how much the retailer has earned by selling those products to the customers. Therefore, this mean value between the demands and the inventory decides how much actual units you can sell to customer. The second part of the right-hand side corresponds to the cost of goods sold. CTI again is the cost term, and we also have a minimum between the action taken by the agent and the actual fill rate from the vendor. And the last term corresponds to the cost of arrival for orders placed. And you can see here we also have this minimum between the agent's action and the actual action coming from the fill rate. So to summarize, the objective is to trade off the various costs incurred and revenues achieved during the period. It generally consists of sales revenue, purchasing, and holding costs, as we see here in this reward function. In more complex formulations, costs including loss of goodwill in the case of missed sales and the terminal salvage value of the unsold items are also included. Once the reward function is defined in MD, it's natural to have the objective function as the expected cumulated reward. And just to have a quick recap, P here is the net revenue, CT is the cost of goods sold, and QT is the cost of arrival. And also we do have certain constraints here. First of all, ATI, that corresponds to action taken by our agent at time T for product I. And in the current simulation study, we only consider the case where ATI is greater or equal to 0, meaning that we only decide whether to buy rather than considering whether we want to remove the inventory. And here a tilde ti is the actual action that goes into the system. Again, it's the minimum value of the action taken by the agent and the fill rate. Let's look at the transition of inventory from t to t+1 as well. So on the left-hand side, it denotes the inventory at t+1 for product I. It is the maximum of two components. The first component in the first part is the inventory at t. It denotes the inventory level when you start the current epoch. And then the second component is the units that just arrived. The summation is over k, where k starts from 0, meaning that the product has 0 lead time, up to t as the maximum value, meaning that the order was placed at the beginning of the rollout. And d here is the demand at time t for product I. Therefore, the inventory at t+1 is the maximum value of all the products that you have hand minus the demand at t. We also demonstrate a sample constraint here, meaning the arrival constraint at time t. The left-hand side denotes all units that arrive at t. So if we do have arrival constraint at t, here's how you can formulate the problem. As you can see, there are so many constraints, so many terms in the objective function. So to start our experiments, we decided to simplify the problem a little bit. Specifically, we revisit the objective function here. Instead of having both cost of goods sold and cost of arrival, here we only consider the revenue term, the actual demand if stock is adequate. I will explain that a little bit more. And the constant C hat. So essentially, we are simplifying the problem by setting Qt equals to 0. Also, here again, AT is the action taken by RL agent. We denote IT minus I being the inventory at time t after the order arrives and before the demand comes. And ITI is the inventory at time t after order arrives and after demand comes. Note that this implicitly assumes that the fill rate is always infinity, meaning that the order amount decided by the RL agent can always be placed and received by the vendor. And QTI is 0, meaning that the cost of arrival is 0. And lastly, as I mentioned, we relax all the constraints. Volume constraint is infinity, capital constraint, arrival constraints, they're all infinity. With all these simplifications, the goal now here is to build a policy pi such that objective function is maximized. Our policy obtains data by acting in a real or simulated environment. However, what we have is a set of historical data from a retailer that has been generated by some policy acting on the words at the time of collection. Therefore, a natural question is, how can we make usage of those historical data to construct a simulator and develop an RL policy? To answer that question, let's first look at some characteristics of the historical data that we have at hand. Historical data tends to be dependent on a policy that was actually managing the inventory. For example, demand is censored for those times where the policy failed to meet customer demand. Therefore, sales becomes the minimum value of demand and inventory at that time. Further policy-dependent data issues might be that the vendor lead time depends on the size of order placed. Unit cost also depends on that size of order placed, and price typically vary within a decision epoch. In a sense, historical data is thus on policy only for the old policy that was managing the inventory, and it is off policy for any RL algorithm that tries to learn a new policy. So how can we turn historical data into a simulator? The answer is that we can try to correct different historical on-policy data by performing different operations, and that corresponds to the actual physics of the word, meaning that we build a simulator by performing statistical operations on the historical data. An online retailer may see signals of a demand other than sales even when an item is out of stock, and this is mostly done by looking at the page views. We can therefore make usage of this view and construct a counterfactual demand signal denoted as d tilde t, and that's actually part of the real function. We do this by correcting for availability, making use of the web page view. Now that we have corrected some of the historical data, we can use it to construct a simulator, and that simulator can be used for training our RL algorithms. We treat each product's demand as a path from some joint stochastic pros with the appropriate context and features. I will elaborate those features in the next slide. And then we roll out a single policy for all products and collect the rewards and use all of those episodes to train our RL policy. So before we look at the actual training results, let's do a quick summary of what the state space and action space are. So state space is the n-dimensional space at time t for product I, and it contains a subset of all the features listed here. The current inventory level, as well as previous actions from the agent. In terms of demand time series features, we have included multiple different features. For example, historical availability, corrected demand, distance to public holidays, historical website view data. And as for the static product features, we considered product group, product description letter, density, and brand. We also make usage of other features, for example, the economics of the product, as well as the outputs of another baseline policy. In terms of the action space, at each time t for product I, it denotes the order quantity directly rather than a target inventory position. This prevents unnecessary dependency on order out policies, which are known to be suboptimal for a periodic review inventory system with stochastic lead times and lost sales. The action can be stochastic or deterministic depending on the learning agent. To represent a stochastic action, a policy that produces the mean and standard deviation of a Gaussian or the scalar action for deterministic algorithm. Products can have orders of magnitude differences in their demand per period. Thus, the policy may have vastly different scales of orders for different products, which becomes a potential problem. To mitigate that issue, we use a baseline policy, and that's actually a version of the news vendor policy, to provide a scaling factor for the current action. We consider the following policies for the purpose of simulation study. First, benchmark against an Oracle policy, which presents an idealized scenario where the policy knows at time t what are the future demands for all the products. In terms of reinforcement learning algorithms, we choose augmented random research, soft echo critic, and A3C. We turn off the agent's exploration during evaluation. And those three algorithms are the top 3 performing algorithms across our experiments. We consider news vendor problem, which optimizes over lead time and demand and a stationary condition as the termination. This produces a classical operations research baseline where the target inventory level is the outcome. Order out policies implicitly assume that the first vendor lead time period sales are fully backlogged. In order to mitigate that effect, we improve the news vendor base stock policy by absorbing extra information of the vendor lead time distribution. Often the planning horizon is represented as the sum of the review period and the percentile of the vendor lead time distribution. We normalize the planning horizon to get the buy-in amount at each time step and manually multiply it by the median of the vendor lead time distributions of all the products in order to approximate the amount required on hand to fulfill demand for a single lead time. Note that all the policies were trained using 2 years of historical data and 19 weeks for testing. So let's look at some results here. Please note that all those results shown are still from simulation study, although we use historical data to build the simulator. First and foremost, the ultimate goal of an RL agent is to maximize the expected discounted cumulative reward. The first panel figure there shows the evaluation curves in which the first value given by Oracle policy is said to be 1, such that all the rest values can be interpreted as the percentage. As expected, Oracle achieved highest cumulative reward at end of the testing period. And all our policies are competitive with or superior to news vendor problem. This verifies that RL indeed can be a good fit in our problem. We also present the sales of RL and baseline policies in the last figure across the testing period. All numbers again are normalized by the value of Oracle at the first time point. It is observed that news vendor and myopic policies tends to buy more, leading to the highest sales value. The significant jump at time point 16 in the sale is due to a seasonal behavior expected by the demand, and that corresponds to the sharp decrease in the inventory level at the same time. We also present the inventory level over time of 2 random selected products here against the demand adjusted by the web page views. The inventory position is measured after supply has arrived and before demand has fulfilled. The trends here are consistent with observations from previous figures. It is worth noting that in the left panel, where normalized planning horizon news vendor problem fails to meet the demand corrected by the web page when the event comes, A3C and SAG have enough in stock. And the right panel indicates that the aggregate behavior of A3C and SAC are indeed similar to that of the news vendor. From the problem formulation to the simulator construction, as well as the experiments results, we can reach to some of the conclusions now. First of all, we have demonstrated that deep reinforcement learning is indeed a candidate solution for solving historical intractable dynamic problems. We developed a novel approach to turning the historical data into a simulator, which allows us to bypass the intermediate system as our word simulator. At the same time, other problems with generous complex counterfactuals may still require more simple, efficient methods, and the application of model-based RL into this problem remains an exciting avenue of research. Great, so this serves as the end of the second part of the presentation. Let's do a quick recap. Recall that this presentation mainly contains two parts. The first part focuses on Amazon SageMaker RL, whereas the second part focuses on the inventory management problem. Please note that while the two components seem orthogonal, they are related in the sense that you can always bring in the created simulator for inventory problem into SageMaker RL to train your RL algorithms. With that being said, Amazon SageMaker removes the heavy lifting from each step of the RL process, and you can easily run and scale your experiments. So hope you folks enjoy the presentation today, and always remember to bring your own RL problem applied to the real world. Again, here's the GitHub link to our public repo. Feel free to check out the examples there, and I'm happy to take the questions in the Q&A session.